Hey, good morning, students. And today we'll be working on logistic regression, which is kind of similar to linear regression. It's still using gradient descent. It's still using a lot of the things we learned in the previous tutorials. The only difference is that now we are using something called sigmoid function. And because logistic regression, even though the name implies that it's a regression, is actually a classification task. And that's lead to us need to change the loss function for classification. All right. So those are the only changes. And a lot of the things we learn in the regression tutorial also applies here. So let's take a look. So right here already, I already prepared some code here. So let me make sure that is run, right? And here during the class lecture, I have introduced a new function called sigmoid function, in which the idea is that we already know this hypothesis function theta tx, which we're gonna give us some value between minus infinity to infinity, right? So the question is there any function in which we call g, in which once we input this theta tx into g, it can output us 0 and 1, right? Which would be very necessary and very appropriate when we do classification. So that's the main question we ask. And it turns out that yes, there's such function and it's called sigmoid function, all right? So let me slowly introduce the term E, the properties of E, and also the sigmoid function, right, through some Python coding. So first of all, the Euler function is something that we have learned since, I guess, since high school or perhaps during our university degree. So let us recap a little bit. How does it really look like? All right. So we can say Euler, right? And I'm gonna just use a lambda in place of any function so that I don't need to give any name for it. So this one refers to this one, all right? And here to keep it simple, I just imagine that this number is any given x and any number from minus infinity to infinity. And so we can easily plot. So we're gonna let x be any number between -5 and 5, and let the step be 1, 0.1, and y is simply the function x, right? And now let us plot them right away. Right. So I think we should, how about we get some title? Right, and x label. And I think this is x, and x label is e to the power of x minus x. All right. So as you can see, given x from -5 to 5, e to the power of minus x will always be a positive number, right? So that is first properties that you need to be aware of this e function, all right? Of course, we can try to put a positive x. We can see that it just is that principle still stands true, right? Because even x is negative, is still positive, and when x is positive, is even more positive, right? So that is always the property of E, and it's always good to remember that E is used across a lot of statistics simply because it's always give a positive number. So it's good way to to do anything related to probability. All right, great. So now once we understand the properties of this E minus X, let us now try to understand how the sigmoid function works, and does it really give us a range between 0 and 1, right? So I'm going to do the same. I'm going to say sigmoid equal to lambda x 1 plus np exp minus x, and this one should, the whole thing should be -1, right? So that is a 1 over, right? By the way, for those who don't like lambda, you can always do something like this, right? It's basically the same. Actually, you don't need to do this. You just say return 1 over 1. 1 plus np exp minus x, right? It's the same, right? And you don't really need this. Okay, but I'm just gonna stick with lambda. This is very cool. Now I think we can plot the sigmoid function right now. So range -5, 5, 0.1, and y equal to sigmoid x. All right, and I may just want to copy this quickly, and sigmoid. All right. So let us, so as you can see, this sigmoid function, the given x that is negative or positive, the range of sigmoid function is always between 0 and 1, right? So this is a perfect function for us to do classification. Now you may wonder, like, what if we have a 2 class? How do we classify? Well, we can threshold it anything below 0.5 to be 0 and anything above 1 to be 1, right? Now, another question you may ask is, what if we have multiple classes like 0, 1, 2? Then we need to modify the sigmoid function into something called softmax function, which is basically based on sigmoid function. But that would be that would be taught in next class. All right, great. So this is the sigmoid function. Now that we believe that it works, how about we take a look at some quick examples so that we know that it really works, right? So let's assume that I have a x that looks like this, all right? And let's say I have theta of 1, 2, right? So now what I'm gonna do is first of all, x at theta will give me a number, right? So this is an example, one sample. So you can imagine that there's a one sample and 2 features, right? And you have theta for the 2 features, right? Right, and you dot it, you get a prediction, which is 11. Now, if you put this inside the sigmoid, it should give you a value between 0 and 1, right? And now once you do that, now you can simply do something like np around and this, then you will know that, okay, given this theta and this x, then this sample should belong to class 1, right? Great. So I think hopefully we got already a good hang of how these things work. The next thing we need, the last thing we need to give attention, and which is very important, is the loss function, which is so recall that the loss function for regression is the mean square error, basically. But for classification, we need to do something called binary cross entropy, right? So the idea is very simple. If your prediction is different from your true what you predicted, then the loss is high. If what you predicted is incorrect, then it should be the loss should be high, right? Okay. Anyway, I think why not we just try to implement this and take a look, right? So we're gonna implement cross entropy. Let's call this CE to be short. I don't want to print too much. And given y and h, and y, the shape of y is simply m comma, and the shape of h is also a vector, right? So you have a lot of predict. This is the true y, right? And you have for many samples, and you also have many predicted y. or we call y hat. That is also fine. And we're gonna have for M shape. So now I'm gonna say loss is equal to minus. So minus is here, and np dot sum, right? And this is resemble this one. And now what I'm gonna do is a y times np dot log h plus 1 minus y np dot log 1 minus h. All right. And having a lot of space is nice to let us see that there's a two equation right here, right? This one and this one, right? Great. So, and then finally, we just return loss. Okay. So now let us try some numbers and see whether how does things, whether this loss function really want, right? What do we want? If the y does not match with h, we want high loss, right? Right. So let us confirm this. So let's say y equal to np dot array 1 1 0 0 1, and let's say I call this bad h equal to np dot array. All right, and let's say that 4 out of 5 of this is all wrong, right? So 0 0 1 1 and 1. All right. So the loss should be very high, right? So let us try this. CE y bad h. Right, and it seems like is this probably because is way too bad? Okay, I think why not we do something like this, right? Because log 0 will give us a very a bad number, right? So we can always do something that really resemble the real world, which is the probability not always like 0 like 1, right? And then we can see that the loss is 18. Okay. So now what if we have a good age? And now we're gonna turn everything upside down. And even though this one is still wrong, but it should be better. So what do we want here? We want the loss to be very low, right? So right, so you can see that the loss is relatively very low. And if we even make this to be like that, the loss is even lower, right? So you can see that this function actually works very well. But if you really want to know and understand the mechanism, either you need to rewatch my lecture video, or you can come to the actual code in the lecture, and you will see that I draw a very nice graph explaining why there's these two functions together, right? What is the intuition? It's actually very important that you understand this, because modern deep learning, all of them use cross entropy, like it's a very basic thing. So you must understand this by heart. Great. So now we understand this. The next thing we need to know is that recall that we have to use gradient descent to find the optimal theta, right? And the way we do that is to make sure that we find the partial derivative of the loss function in respect to the theta, right? And I already do all this math for you. So let's say J, the loss function is this, and H is actually another function inside, and G is actually another function, right? So it's actually a chain rule of 3 functions. And if you do the math correctly, you will find that this is the gradient, and it happens that it's share the same gradient as linear regression. For those who want to have the full derivation, again, come to my lecture here, and I already provide you a lot of recap how to do derivatives. And if you brush up your calculus a little bit, you should be able to understand how I do all these derivatives, right? So that's that. So I think now we are ready to actually implement our algorithm. So right here, I already prepared the basic thing for you, so you don't need to have the code. So it's based, the only part that is changed from the previous tutorial is that now I'm not using diabetes. I'm using a data set I created using make classification, right? Right here, I have 500 examples, 10 features, and then some of the noises that I add to make sure that it's not exactly straightforward, right? So why not I punch this? And then, so this is how the data looks, right? And hopefully logistic regression can draw a line around here, right? And try to see that and classify accordingly. Yep. Great. So that is the prepared data. Why not we now begin our training, right? And there are several things we have to do. First is fit, grad, Sigmoid, predict, and output, right? So as usual, let us get our confidence up by doing something that is quite straightforward, right? So we are ready to learn the Sigmoid. Why not we try the Sigmoid first? So Sigmoid x return 1/1 plus np.exp minus x. All right. And in the next one we can quickly do is the prediction function. And return sigmoid and theta, right? So that should be our prediction function. Please note that this time I'm again not writing as a class, but if you take a look at my second tutorial, actually I teach you how to convert into class, right? The only reason why I'm not implementing in class is to make sure everything is very clean and simple, but make sure that when you actually implement your own algorithm, you want to put them into class. And once again, what I'm teaching is purely for understanding, and you should not use this in industry. You should use all the API like sklearn that is already available, and they works much better than mine because they optimize, etc. But this is for you to understand the mechanism. Output is very straightforward too. So we just make sure that output, and given the prediction, we want to just return the round of the prediction. Right. Okay, I think it should be NP round. All right. Gradient, yes. So for the gradient, given x, y, and w, let us take a look, right? The gradient is nothing but the x dot t dot with h minus y, right? So first of all, what we can do is m equal to x dot shape 0, right? Recall what is x, right? So x is the shape is n comma n. So, and then y shape is n comma. And then what we're gonna do here is okay. So actually we can do the x. We can do the gradient function. I mean the prediction in the fit, or we can also do it in the inside the gradient function. How about this time we do it everything in the gradient function? So we're gonna say that h is equal to predict x and w. So once I call this, it will call the sigmoid, and I'm gonna get a predict y. And what I need to do is I want to say that the gradient, right? The gradient is nothing equal to x dot t dot with h minus y, right? So that should be good. Now, I also want to return the loss in the fit function. So why not I just calculate the loss anyway? So I'm going to say loss equal to minus np dot sum y times np dot log h plus 1 minus y np dot log 1 minus h, right? And in this function, what you're going to return is the the loss and the gradient. Okay, okay, great. So it seems like I am not using the m, right? I can do like this, right? Divide it by m. So now I'm using the m, and that thing should be good now. Great. So now I am ready to write the fit function. For the fit function is quite straightforward. So I can take the x and y and max iteration equal to 1000. And what I'm gonna do is I'm gonna say that the theta is equal to np dot 0 and x dot shape. So theta should be, the shape should be features, right? N, right? So it should be 1. And now what I'm gonna do is a learning rate is 0.01. And the batch size is let's say 0.1 times x dot shape 0, right? Just some number. I guess there's a 500, right? So that would be 50. Yep, the batch size is 50. And then what I can do is for I in range max iter, okay, here I want to do epoch, right? So I need to this time I'm gonna change a little bit. So I'm gonna do randomly pick some integer. Okay. So what this function does is it's gonna randomly pick an integer, right? And then what I'm gonna do is I'm gonna say that this mini batch x is equal to x from this ix until the batch size. Yep. Right. And so I'm doing actually mini batch gradient descent. And this mini batch y is simply that y. And I don't think I need to do comma here column because the Python should be able to know. One thing I need to add is that previously we did not do a randomly pick, right? We looped through the whole data set, 0 to 16, 17 to something like that. So it's like gradually finish the whole data set. That is something called without placement, replacement. But here I'm randomly choosing. So this is called with replacement. So with replacements means that the mini batch could actually be could actually repeat, right? There's no right or wrong whether which one is better or worse. But I just want to demonstrate two ways. But I can say for deep learning that the common way in deep learning, we just simply do without replacement. That is, we just simply go 0 to 16 and then 17 to what? 32, right? And then 33 to etc. So that is without replacement. But this time I'm doing with replacement, just for the sake that you also know that there's with and without replacement. So now what I can do is all right. And so now we got this mini batch. So we just say that loss gradient is equal to gradient of x mini y, and then theta. All right. So actually, I should call this theta to make sure that things are consistent right here. I don't want to say sometimes I call W, sometimes I call theta. Now, I can now actually print something. So I'm gonna say that for every 500 iteration, please print the loss, right? And the loss iteration I is nothing but this loss, all right? And then after I do that, I will update here. I would say that theta is equal to theta minus LR times graph. All right, and then I'm gonna say return theta and I, so that I know how many loops does it run, and I will get the final theta that I can use to predict something, right? Okay, so let me check whether I'm correct. Yeah. So max iter, blah 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 blah. The reason why I don't call this epoch anymore is because I don't know whether it's exhaust the data, right? So I rather call this max iteration. But if we do without replacement, in which we go one by one, we know that when one does one epoch finish. Okay, great. So I think that should be it. So why not we close this? Okay, give me 1 second. Okay, now I should be able to close. No. All right. Anyway, give me just 1 second. All right, great. Now I can actually use my code to test the accuracy in the testing set, right? So what we need to do is first train and then test, right? So what to train is actually very straightforward. What we do is we're gonna say that fit, and then the x train, y train, and then max iteration is basically 5,000. And then if I'm not wrong, what does it return me? It returns me the theta and I, right? And let me just make sure that it runs. All right. So it say that cannot access local variable grad when it's not associated with a value. All right, great. So give me just 1 second, and then I will be. I don't need to pause. I guess it's very clear, right? That this function name is the same as that, right? So why not I just say that gradient function, right? And then that should be fix everything. Yep. All right. So I need to run everything again, clear offer, restart run all to make sure that things are fine. All right. So seems like things are fine. I got my loss seems to be gradually reduced, but yeah, only from the beginning, right? But it seems like it's got good here, and then it got worse here, right? So usually the good practice is if your loss is really good, you would want to save that model, right? So that is probably the right practice. And so, all right. By the way, for those who want to save, you just use pico.save, something like that. And you can look up the tutorial at online how to do that. It's actually very simple. But let's do the testing. So what we're gonna do is y hat equal to so first of all, we want to do predict x test, and then theta. So now we got this new theta, right? And we want to, actually, I should not put it in the same cell, otherwise it's going to train again. And then I want to actually round this, right? I'm going to call this output function. And now I can actually see this y hat, right? And now how do I know whether it's good or not, right? Well, we can actually use sklearn.metrics, import accuracy score, and then we can just punch in accuracy score, y tests and y. Okay, give me 1 second. I don't remember whether you should put which one in the front. Y true in the front, right? So y true is a y test and y hat. Great. So it seems like our accuracy is 0.76. Not so bad, right? In fact, it's not so bad. So I just wondered if we trained even more, like 10,000, does it get better accuracy? I just wonder. Yeah. Okay, so seems like it's better, but I'm not sure whether it's by chance or whatever, right? So yeah, so I think logistic regression is quite similar to linear regression. It's still using gradient descent. The only changes is the basically the I would say the loss, the gradient, how you calculate the gradient, right? Which is actually the same, I would say, but the difference is the loss function, right? And the sigmoid function, which is changing the prediction function. All right. And yeah, logistic regression is a very important algorithm, even until today, until all the modern deep learning classification somehow related to this logistic regression. All right. Thank you very much and see you next time. Bye-bye.